Okay, welcome to logic. So we're starting the next section in our book, and let's talk a little bit about kind of the process of understanding logic. This, more than anything else that we do in this class, is kind of the abstract part of learning. Abstract meaning it's not concrete, it's not clear. There's not, for many of these questions that you're going to be asked to do, there's not like an answer. There's not just one way to say something logically. And that's okay. It's confusing and it's murky, and that's normal, perfectly normal. All right? The important thing is that we work through this process. The mental skills that you're going to get by working through this will help you later on, trust me. All right? Also, remember that with logic, okay, you're going to need to ask questions. You can't just read the book and watch these videos and expect to just click. That's not going to happen. You're going to have to talk about it with me, with your fellow students. And what's going to happen is you're going to be confused. You're going to ask some questions. We'll kind of go back and forth, and you'll be like, okay, that's starting to become clear. And an hour later, it's gone. And that's normal. That's part of the process, okay? Don't worry about it. We just need to keep pushing through. It requires a little repetition. And also, I highly advise, as you go through these lessons and as you go through the book, be working on that vocabulary list, because what makes it really challenging is to not have a full grasp of the vocabulary. And this more so than any other unit because it's so murky, right? So when I say terms like inverse, contrapositive, you should be writing that down. And you should be, adding that to your little vocabulary, and you should have it right next to you. Also, those rules, right? That we have, the distributive rule, the De Morgan's, all of that big list of rules. You should have that next to you always as you're going through this stuff, particularly while you're doing the homework, but also while you're watching the videos, so you can refer back to that. All right. What different symbols mean. At certain points in the next section, comma means such that. And it doesn't say that. It just says comma, and you have to know that means such that. All right? So be very vocabulary focused on this one. Understand that it's going to be a tough process, and let's go. So when we're talking about logic, we're talking about the, for lack of a better term, truthiness of something. How true is it? When we talk about propositional logic, we're talking about things that just are true, right? And mostly with propositional logic, we're interested in how do we state the truth, okay? We're looking at the structure of the statements. And they don't have structure in the same way that English does. English has different parts, nouns, verbs, adjectives. There are no parts to a logical statement. They're just substatements and how they're interpreted, which makes it a little bit more confusing. It can convey less information. So certain things that are very easy to convey in English become very difficult to convey with propositional logic, and that's okay, because propositional logic is just one tool in our toolbox. And mostly we're interested in understanding the structure of these statements and the order that things are evaluated in. We're interested in manipulating them, mostly to reduce them to simpler examples, and ultimately, in many cases, to reduce them to 0 or 1, which will be a contradiction or a tautology, which we'll talk about a little bit later on. So that's propositional logic. That's our most basic logic. That's mathematical logic. Then you have prepositional logic. In prepositional logic, we try to map real-world statements to logical statements and prove things about the real world. I don't know how useful it is in the real world, but it's more broad than propositional. So prepositional allows us to add qualifiers, right? So instead of just saying this is true, we can say this is true with these restrictions, right? Mostly the restrictions are, for all, this is always true, or, at least once this is true. That's our next section. We're going to talk about prepositional logic. This unit's all about propositional logic, but I want you to know kind of how they go together, and how all of this builds off of Boolean functions. right? All of this is directly related to the work you did on Boolean functions. So if you're a little shaky on Boolean functions, you might want to go back and brush up on that. And if you need some extra practice problems, I can give you those too. Because, yeah, everything we do here builds directly on top of that. We're going to be shifting things around a little bit. So whereas in Boolean functions, we talked about 0 and 1, when we're talking about propositional logic, we use false and true, even though they have essentially the same meaning. Whereas we were talking about Boolean functions, now we're really talking about logical statements. And, you know, your book lists a few other ways that what we did in Boolean functions maps to propositional logic. I'm not super concerned about the details. I just want you to understand that everything we did before still counts. None of it goes away. That's the important thing. We're concerned quite a bit with form when we talk about logical statements. And I want you to understand the difference between form and structure. Structure involves an ordering of things, and the ordering provides meaning. For example, okay, so we all know that the subject in this sentence is the dog, because the dog is doing the action. And we know that because it's the first thing. And we also know it by the case of the action, right? Bit instead of has bitten, you know, they're bitten, well, has bit. There are a few different ways we can phrase the action that might indicate who is the subject. But we know, based on the ordering, that the dog is the subject here. And we know that the man is the object because he is the one that's acted upon. That is the structure of the English language, and none of that exists in logic. In logic, the structure doesn't matter whatsoever. So whether the P is in front of the Q or the R is in front of the whole thing, that doesn't matter. There are still rules based upon the parentheses and and ands and ors and whichever actions we're taking. There are still rules, but there's not structure in the way that we would define it for the English language. By the same token, this all relates to things that you have seen before in high school. Remember this? Remember, x squared plus 3x minus 2? That is the form that you would write a quadratic equation in your math class. Remember, the exact same thing could be written as, so those two algebraic equations are the same. Well, they are what we would call logically equivalent, but they have a different form. That becomes very important when we're talking about propositional logic. For example, so we know that this statement is the logical equivalent of that statement due to the distributive rule, right? We know those two are the same. We just distributed R into the parentheses. So they are logically equivalent, but they have different forms, right? That's an important concept we need to be aware of. And notice that it's not really the same in English. I can't have another sentence for the dog with the man that really has the exact same meaning without adding to it and thereby changing the meaning. So when you have structure, the structure actually changes the meaning. Whereas when we don't have structure, two things can have a different form but be logically equivalent. How do we know in propositional logic if two things are equivalent? Look at the truth table, right? That's the only way to be sure. Okay, a few more terms we want to get straight, or really a few terms that mean pretty much the same thing and we want to know where they don't. First of all, we have our good old equal sign, right? We know what equals means. It means these two are the same. Sometimes in propositional logic, we'll actually write out the term equals. And that is because that we do that when this equal sign is not appropriate. This actually comes up more in prepositional logic because when we define prepositions, we're usually defining a function. And oftentimes we say the output of a function is equal to something else. So that's using equals in a mathematical sense. So when we sometimes don't want to use that again to say that two logical statements are the same, so we'll use the word equals. You will also see that. And if you have that with P and Q, what you mean is P implies Q at the same time Q implies P. Which is not exactly the same as equals, but for all intents and purposes, it's equals, right? Logically, it works out to be equals. As a matter of fact, let's take a look at the truth table now. Okay, so let's take a look at, let's review a few of our old Boolean equations. Obviously, not P is the reverse of whatever P is. That one's pretty straightforward. P and Q is only true if both P and Q are true. So for all other cases, it's going to be false. P or Q is going to be true if P is true or Q is true. So in those cases, it's all true. And now let's add another column, P equals Q. Put that in quotes there. So P equals Q is true if and only if P and Q are equal. Is 0 equal to 0? Yes, it is. So that's true. Is 0 equal to 1? No, it is not. Is 1 equal to 0? No, it is not. Is 1 equal to 1? Yes, it is. So P equals Q is true if and only if both P and Q are equal. And that's, obviously, we're using it in that sense. We're defining it, so that works. Is it equal in that sense? Yes, they are equal in the mathematical sense. Is it equal in that sense? It is, and that will become clear when we talk about implication, right? Because what that means is P implies Q and Q implies P, which basically means if P is true, then Q must be true, right? Which is true here. And then if P is false, then Q must be false, because if Q was true, it would make P true, which is kind of circular, but it'll make more sense once we talk about implication. Trust me. All right, one final thing I'd like to point out from this section is Theorem 1 from your book. That should look familiar. It's exactly the same thing we were using in Boolean logic, except when we were talking about Boolean functions, we use the equal symbol, and now we use the double implication symbol. But remember, it's all the same, right? The double implication is exactly the same thing as saying equals, except in situations where you're using equals to mean like mathematical equals, like 5 equals x. Or, excuse me, let's say 25 equals x squared, right? In that case, we're using equals to mean something, so the implication becomes useful. And in propositional logic and prepositional logic in the next section, we do that a lot. That's the only reason that those have been switched to the double implication. All right? Okay. In the next video, I'm going to talk about example 1 and go over that. If you have any questions, ask them in the forum below.